double integrals and finding area. So a double integral is as it sounds. We have two integrals. In this case, we want to integrate dA, that is delta area, over a region R. For example, let's say we want to integrate from 0 to 2 and then 0 to 1 of dx dy. So a few notes. In mathematics, we work our way inside out. So I could put parentheses here, sort of. It's not being multiplied, but just kind of make it a little bit more visual what's happening. So we have an inner integral, which is 0 to 1 of dx. And then an outer integral, 0 to 2 of whatever this is, dy. Let's start by getting an intuitive understanding of what we're trying to do. For this double integral here in our example, I drew the picture of what's happening. We have x going from 0 to 1. So x going from 0 to 1. And then y is going from 0 to 2 over here. So I have a rectangular region. This is saying all x is 0 to 1 with all y 0 to 2. And then I broke down my region, this rectangle, into a grid. Now really, dx and dy each are infinitesimally small, but I drew them a little bigger so we could see it. And then I magnified one example over here, just so we can see that one of these squares or rectangles, that is one of these broken down ones, part of my grid, has an area of dx times dy. So let's go back up to our integral over here. And note that we're starting on the inside out. So what does this mean? Okay, it means let's fix a y value. So let's fix like y equals 0 or right about y equals 0. So we're over here in our graph. And then, and I'm going to go back here and rewrite this one because the parentheses are there to help us kind of break down the order of operations. But what I'm really doing is integrating dx dy. So I fixed a y value, say 0, and then I'm going to find dx dy at my first x, and then I'll go to dx dy at my next x, if you're watching me fill in this grid over here, then dx dy at the next x, etc., until I get to x equals 1. And then it says sum the areas, right? This inner one is the sum of all these dx dy's in my first row. Okay, well now let's go back to the second integral, the outer one. Let's go to our next y. So say right here, right above that one. And we're going to repeat the process. I start at x equals 0, and I find the area dx dy. Then I go to my next x, find dx dy, etc., etc. And then I sum this next row. And I keep doing it up and up and up until I get to my final y value. So this inner integral is saying, let's find the sum of each row. And this outer integral is saying, let's sum the areas of all the rows. Now, we'll extend that when we get to double integrals and volume, but the idea there is still the same. Now, what I found working with students, the part that seems to confuse students the most when we're doing double integrals and triple integrals is finding limits to describe the regions. The process of integrating is usually not that difficult, but it's how do we find these limits? So consider my graph here. I have the line y equals x, And then region 1 is going to go from x equals 0 to 1 and then y equals 0 to 1, but beneath my graph y equals x. How would I find the limits of this region? So I started here with dy on the inside, which means I'm going to do y's first. So what do y's do? Well, we're going to fix an x. So let's start at this x value over here. And what do my y's go from? Well, they start at y equals 0, and they go up until I hit y equals x. If I had picked a different x value, it doesn't matter. I would start at y equals 0, and I would go up until I get to y equals x. So instead of doing areas of rows first, we would be doing areas of columns. Something like this. Now I need to add all those columns together. So where did I start making the columns? Well, I started making them at x equals 0. And I stopped making them at x equals 1. So this would describe the region R1. What if I change the order of integration? We call these things iterated integrals. I might throw that in sometimes, but we're changing the order of integration here. What if I started with x first? Okay, so I'm starting with x first, then I'm fixing a y value. So I'll just pick a y value over here. Where do I go? That is, where do I start and where do I finish? And if I go up again, am I starting at the same thing and ending at the same thing? It might not be the same number, but it might be the same function. So for every single one of these y's, do you see how I start at x equals y and I end at x equals 1? All of these start at x equals y and end at x equals 1. Now where did I start making these rows? Well, at y equals 0, and I stopped making them at y equals 1. So when you change the order of integration, you don't simply swap out the letters. You have to kind of think about what's happening so that we can get the limits. So let's do region 2, which is going to be the same picture, except region 2 will be this side of it. What if we want to integrate y's first again and then x's? So if I'm starting with y's, I'm fixing an x. And let me change the color here so we can see it a little bit better, hopefully. I'm fixing an x value and going from this y to this y. Fixing the next x value, going from this y to this y, etc., etc. So what would my limits be for y? Well, I start making these things at y equals x, and I stop making them at y equals 1. And I started these columns at x equals 0, and I go until I get to x equals 1 way out here at the end. What if I change the order of integration here and did x first? So if I do x first, I'm fixing a y value. Let's make that blue. Hopefully that'll work well for us. I'm fixing a y value and going from this x to this x. Then another y value, x to x. Y, x to x, y, x to x, etc. So which x did I start at? Well, I always start at x equals 0, and I always end up at x equals y. And once again, my y's are going from 0 to 1. How about this one? What if I want to do a double integral to find the area shaded that makes that triangular region? Well, let's fix a few things or put some extra information in. This would be y equals 2. You can confirm they intersect there. And this over here would be x equals 2, then 4. So let's find the double integral starting with y. So if I want to integrate y's first, I'm going to fix an x and then go from y to y. And then fix an x and go from y to y. And then fix an x and go from y to y. Did you see what just happened there? If I'm doing y first and fix an x over here, I have a y value to y equals x. But when I get over to this side, I go from a y value to y equals 4 minus x. So I'd actually have to split this into two separate double integrals. But what if instead we simply switch the order of integration? So I'm going to fix an x value, or I'm going to fix a y value and do my x's first. So x to x, x to x, x to x, etc. What if I do that? Well, then I don't have to do two separate double integrals because I'm going from the first x, which is y, to the second x, which is 4 minus y. And then my y values are going from 0 to 2. So we're not evaluating these yet. I just want to set up some regions because that's the part that seems to trouble students the most. Now let's do one more. But in this case, I'm giving you the double integral. And we want to draw the region that's associated with it. All right, so what kind of picture should we draw? We'll get the axes going here. Well, I know that I have the graph y equals x squared because I'm going from y equals x squared to y equals 4 because we start in the y's. So I'm going to go ahead and draw the graph y equals x squared. Something like that. I'm going from x equals 0 to x equals 2. So over here, which does give me y equals 4. Now, it could be this region over here below the graph, or it could be the region up here above the graph. Well, which one is it? Well, let's see what it says. It says we're starting at y equals x squared. So the lower bound is y equals x squared. So the lower bound is y equals x squared. And then we go up until we hit y equals 4. Should have started here at x equals 0, y equals x squared to 4. Then the next x, y equals x squared to 4. Then the next x, y equals 0 to 4, etc., etc. So the region in question is that one there. Do you think you can find the limits if we change the order of integration? What if we do dx dy? Well, x first says we're going to fix a y value. And then go x to x. Fix a y value, x to x, etc., etc. So what is my lower x value? Well, my lower x value is always 0. And my upper x value is what? Is it x squared? No. My upper x value is x equals the square root of y. And then my y's start down here at the bottom, that is at y equals 0, and we go up to the top, y equals 4. And those would be the limits if we change the order of integration.